Okay, in today's lecture, we are going to talk about flow description. Okay. But I would like to begin with one example from previous session. In previous session, we talked about Newtonian fluids, and we learned how to use viscosity law, Newton viscosity law. This is an example about Newton viscosity law. Definitely you will have one question from this equation in your midterm exam. The question says the space between two square flat parallel plates is filled with oil. Each side of the plates is 60 centimeter. Each side of that plate is 60. So the thickness of the oil film or oil layer, film here means layer, is 20.5 millimeter. The upper plate, which moves at 2.5 meter per second, requires a force of 98.1 Newton to maintain the speed. Simply summarizing, two plates we have. The upper one moves, the lower one is fixed. Between these two layers, thickness is 12.5 millimeters, and the velocity of the upper layer is given, and the force that creates this velocity or this motion is also, the force amount is given, 98.1. The question asks, 1, determine viscosity of the oil, okay, then determine a dynamic, and in second part determine kinematic viscosity of the oil. And also the specific gravity is given 0.95. Do you remember specific gravity? What was it? The ratio of density of any liquid or any fluid to the density of water. So this is a dimensionless parameter, which is called specific gravity. Okay, let's see the solution, which reminds you the entire formula of the Newton viscosity law. Again, as usual, we summarize the information at the left side. As you see, we have a plate 60 centimeter each side. Therefore, the area can be found easily. It should be 0.36 meters square. We have the area, the thickness D between two layers, or thickness of the oil is 12 millimeter. We are solving every problem in SI unit in this course. Therefore, our thickness is exactly equal to 12.5 times 10 to the power minus 3 meter. And the question says the lower plate is stationary, the upper one moves. So we already talked that when a liquid moves, we can assume that several layers of liquid moves one above each other. Look, so if this upper plate moves as a result of the given force, therefore this layer of water moves. Then the second layer moves. The lower, the middle one, and at the bottom, we told that the bottom layer never moves because of non-slip condition. Non-slip condition that we said always the bottom layer does not move. So you see that this is this graph that you see here. Okay, this line. What we call this line in previous session? Do you remember the name? The name was velocity profile. You remember? This is velocity profile, and we solved an example when we had a curve like this as a velocity profile. However, in this question, we do not consider the velocity profile. We can use directly the formula. And one important thing that here I would like to talk about it is the transformation of this equation to mu over dy to the one that you see here. Okay, that you see here, and in the middle of the solution I will talk about it more. But in general, this is our formula. We do not have tau, but du over dy were given. What was the name of du over dy? Do you remember the name of du over dy? Do you remember the name of this part? We already said that this is velocity gradient. This is velocity gradient. And here you see that I have velocity profile. So do you remember what does the gradient means? What does the gradient mean? Gradient means?
It means the change, we can say. Basically.
Mathematically, I said gradient means tangent, yes?
Yeah, tangent also.
Tangent. Therefore, if you calculate tangent of this angle, so let me show the angle again. If you calculate the tangent of this angle, you can find du over dy. And we know that this increase seems linear, yeah? Linearly increased velocity. Therefore, you have a triangle here. You have a triangle, and the tangent could, instead of du over dy, you can say u, or this side, over d, or u over y. In some cases, we show y by d, which both shows the thickness of the fluid. So instead of du or dy, we can use what? U over y. 2.5 here is u. We have u and dy. The question we summarize as a dy, but in general it could be considered y, not dy. The thickness. The important note that I want to emphasize it, when the velocity profile is linear, instead of du over dy, you can use u over y. Because du over dy exactly equals to u over y. Can anyone show me du over dy in this figure? I'm going to erase everything. Okay, can you show me du over dy? Okay, let's come back to the first one. Can you show u over d? Yes, you can. This let me show you u over d. Okay. You agree that the plate moves with the velocity of u. Am I right? The question said the plate with the velocity of upper plate. So this is u. This, assume that this arrow shows this arrow shows u. This is u. Okay. And I asked you u over d. U over y, sorry. And this is my y entirely. So this is u, this is d. Therefore, u over d is clear. This side over this side. And if I draw this linear line, u over d is what? u over d is exactly equals to tangent of this theta. Tangent of theta equals to u over d. Here I would like to show you du over dy if you don't know now. If you know, you can answer. Let me show you du over dy. Just I'm going to make a bit clear everything here. Okay, du means difference of u, or relative velocity. What, if you remember in previous session, I said that if this is u, this is velocity at one layer below, and I can show this small triangle instead of entire one. Therefore, this side is du, and this thickness of this layer is dy, yeah? This side is dy. Because, as I told, as or since the big triangle or the velocity is linear, exactly du over dy equals to u, this value, over y. Or this smaller triangle is similar to the bigger triangle. Therefore, in this question, instead of du over dy, we can use u over y. But first we have to calculate tau, because the question only gives us the value of f, this value. You know that tau equals to force over area. Yes, tau equals to force over area. And therefore, force is given, area already calculated. The value of tau, or shear stress, is at hand. Now we are looking for mu, and we know that du over dy equals to u over y, u already given, 2.5 meter per second, you see here, and y 12.5 times 10 to the power minus 3. And if you solve this equation, you can find mu, which is dynamic viscosity. You remember the unit is Pascal second or Newton second per square meter. So we solved the first part of the question. For the next part, or for the second part of the question, the question asks us to calculate kinematic viscosity. You remember I introduced you this formula. Nu equals to mu over rho. And now we have mu. We need to find rho. And we don't know the density of oil, but we know its specific gravity, which was what? Which was 0 point, here is given, yeah? Specific 0.95. If you multiplied it by the density of water, which is 1000 kilogram per cubic meter, you can find density of oil. Easily divide mu by rho, you can find kinematic viscosity, and you see the unit is meters square per second. So by this example, we summarized Newton viscosity law, and we see that when the velocity distribution like as in this figure, is linear, velocity distribution is linear, it is not curve. Let me show again a curve also. Okay, and if the velocity distribution is curve, it should be something like this. Okay, the upper velocity is this, and you see that velocity at different layers does not increase upward linearly. So when the velocity profile is linear, instead of du over dy, you can use u over y, and the reason is the similarity between these triangles. Look what will be happen in nonlinear or curve shape. I would now, if I, instead of this curve, if I connect the zero velocity to the maximum velocity linearly. Look, I connect linearly. I assume this is a linear line, okay? Look, there are considerable difference between this curve, and this linear line. This is why here I cannot say that du over dy equals to u over y. And you have to apply exact derivative of velocity curve of this curve with respect to the y to find du over dy. Okay, so dimensions and units. As I already told, we will use SI, System International Units. Fluid mechanics deals with the measurements of many variables of many different types of units. Hence, we need to be very careful to be consistent. It means that use consistent units. Don't select one unit from SI, another unit from metrics. When you use, for example, velocity in meter per second, distance or thickness should be in meter, not in millimeter, as you saw in the previous example. Dimension, it should be consistent. Both sides of equations should be consistent. Dimensions and base units. Yeah. The dimension of a measure is independent from any particular system of unit. For example, velocity may be in meters per second or miles per hour, but dimensionally it is always length per time, L over T. L denotes length, T denotes time. The dimensions of the relevant base units of the system are now I'm showing you the primary units, which is MLT in SI system. MLT, M for mass, M is the symbol for mass, L is symbol for length, and T for time. Also, we have theta for temperature. These are our main or first entities. We say what first entities or first degree entities. If we mix these first degree entities, we mix by multiplying, by adding, by dividing them together, new quantities, new entities, or new quantities like velocity, acceleration, force, blah, 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 can be generated. For example, if you divide length per time, it gives you velocity. Therefore, we say these are secondary quantities. These are initial quantities or entities, and you know that what is the, for example, unit of mass in SI system? The unit of mass is Aras Aktaş. Okay, Makbule, what is the unit of mass in SI system?
Kilogram.
Kilogram, yes. For length, continue, Makbule, please. For unit of length is? Meter, yeah. For time?
Second.
For temperature?
Kelvin.
You are right, you are right. So, when you multiply or divide these primary units to each other, you can find the units of secondary quantities. As I told, for velocity, we divide length by time. Therefore, the unit is meter per second. For acceleration, you divide length by time 2 times, or 2 times of time, or a square of time. Therefore, the unit is meter per square. And these are basic things that you know. And just I want to show 2 new or 3 new quantities that you might were not aware about it before this course. In this course we talked about density. The unit is which can be shown with the dimension of ml to the power of -3, and also dimension of viscosity is ml to the power ml minus 1 t minus 1, and the unit of viscosity was Pascal second, yeah, Pascal second. For density, kilogram per cubic meters in SI system. So try to find for yourself, okay? Find different secondary quantities like force, tension, specific weight, and some other things, energy, and find their dimensions and calculate their units and try to memorize it. For example, for density, for viscosity, kinematic viscosity, dynamic one, you should always know them, because in that way you can quickly answer any question that you have. Now let's talk about the classification of fluid flows. Based on different features of flow, we can classify fluids in different categories. Here, the feature of velocity is considered, and then we classified flow into laminar and turbulent flows. You see, as I told, we can assume that when the velocity is very low or the thickness of fluid is very low, we can assume that water molecules or water elements or water molecules move in a thin layer and with a regular pattern. You see, for example, one layer here, different layers moves without any turbulence, without any chaotic or random replacement. And it seems that every layer moves on above it. And in that case, we say the flow is laminar flow. Some flows are smooth and orderly, while others are rather chaotic. The highly ordered fluid motion characterized by smooth layers of fluid is called laminar. The flow of high viscosity fluid, such as oils at low velocities, is typically laminar. Okay, so when we see that the thickness is low, for example, oil within the a piston of a car, you know, and a piston moves upward and downward within a cylinder, yes, and around the piston of a car we have a thick layer of oil, and we can assume that or we can say that the flow of that oil is laminar. When the motion is highly disordered, like here. You see the motion is highly disordered or is chaotic, or you cannot trace motion of a water molecule. For example, assume this is a water molecule at time 0. At time 1, after 1 second, it's here. After 2 seconds, it moves here. After 3 seconds, it moves here. 4, here. 5, here. 6, maybe here. 7, here. And you cannot know where is it. And the motion is really chaotic, not such a laminar. At laminar, you see the molecule moves directly on the same layer, on the same line, which is called path line. The line that shows one water element, location of water element by time, through the time. So in that case, which the motion is turbulent or chaotic, we say this is turbulent flow. And we have also a transitional flow. This one is a transitional flow, which is not laminar and also not fully disordered, fully chaotic. And maybe water moves in, one molecule moves in that way. You see, it is not linear. It is not. It moves in the up layer, comes to down layer by time, but it is not fully disordered as we have in turbulent flow. So the flow of low viscosity fluids such as air at high velocities is typically turbulent. Air at high velocity is turbulent. Yeah. A flow that alternates between being laminar and turbulent is called transitional flow that you see here. Okay, what is the metrics? What is the index to find which kind of flows we have? Actually, the metric is Reynolds number, but it is discussed later in chapter 5, not here. Here, just you should know that when velocity is low, a thin layer of water moves, it is, or viscosity is high, it could be laminar flow. In general, most of the flows in pipelines is turbulent flow. In nature, in rivers, turbulent flow. Okay. So here we have another type of classification of fluid flows, which is called natural, or in front or versus the forced flow. What is the natural flow? A fluid flow is said to be natural or forced depending on how the fluid motion is initiated, depending on the force. What is the initiated force? Initiated, or what is the trigger? A force or shear stress, okay? And shear stress as a result of a force. In forced flow, when say the flow is forced flow, a fluid is forced to flow over a surface or in a pipe by external means such as a pump or a fan for air. It is called forced flow. For natural flow, any fluid motion is due to natural means such as the buoyancy force or buoyancy effect. We will talk next chapter, which manifests itself as the rise of the warmer and thus lighter fluid and the fall of the cooler fluid. And about this also we will talk on hydrology also. Okay, when the force is natural, like gravity, it is called natural flow. Flow in rivers is generally natural flow because the water elements moves as a result of gravity force, not as a result of extra pumping or any other force. When you pump water from a well, you use extra force. It is called force flow. Okay, so laser point. The other class of flows are called steady flow in front of unsteady flow. We talked about steady and unsteady flow in our hydrology course, but here you can see that the term steady is used when there is no change at a point of fluid by time. For example, you have a water motion within a pipeline. We know that there is a pipeline and water moves. And in one point of that pipeline, at different times, the velocity is constant, for example, or its pressure is constant. It is called steady flow. By contrast, if at different times, the flow characteristics, such as velocity, varies, it is called unsteady flow. For example, in our pipeline, in one point, there is change at the velocity. Can you guess how we can change the velocity of water in a pipeline by time? Assume that
we can change the properties of the pipe to be able to change the velocity.
No, for the fixed pipe. We have a pipeline, but we know that the flow within it is unsteady. It means that velocity by time at the same pipeline changes. How we can make such change?
Maybe it is being pumped from somewhere, that's why.
Yeah, okay.
I mean,
by pumping, if the constant amount of discharge pumps, maybe it could be steady. Because when you pump, a constant discharge is pumping. Think about this. Okay, let me draw to you, and during this drawing, you can think. I have a pipeline like this, and water move. This is water moves within pipeline, and at this cross section, at this section, I have, for example, velocity meter, so, a gauge that shows me the velocity. Okay, velocity, and I see that velocity change by time. I can show in that way. V is a function of t. How it possible? Simply one way is if you have for example, valve here. If you open and close the valve, the velocity increases or decreases by time. When you open the valve, velocity increases. When you wash your hand, what will happen? During the opening the valve, velocity from 0 increases up to the maximum in the faucet. Okay? And during the washing your hands, velocity is constant. Yeah. Therefore, you have a steady flow. At the end, again, you use when you closing the valve, velocity starts to decrease from the maximum to be 0. Therefore, during the closing, the flow is unsteady. The other category that we have for flows is uniform flow and non-uniform flow. When we have no change at the length of the pipe or length of the flow, it is called uniform. For example, assume this cross-section 1, and this cross-section, I say cross-section 2. Within this distance, if within this distance, for the given time, fluid features like velocity of fluid, like pressure of fluid, is constant, it is called uniform flow. If it varies, it is called non-uniform flow or varied flow. Okay, now in this figure, what do you think? Is it uniform or non-uniform? Any idea?
It is uniform.
It seems to be uniform now, yes? It seems to,
yeah.
Because for example, if we assume this is, for example, 10 centimeters. 10 centimeters before, 10 centimeters after, in a pipe with a constant diameter, there is no change in the velocity. Even if the diameter is constant, instead of 10 centimeters, you say 1 meter. Again, velocity, everything is constant at both section 1 and 2. So we say this is uniform. For how it could be non-uniform, what we should do to have non-uniform flow? Just wait.
Okay, we're waiting for them to think.
They think, yeah. Okay, let's ask Akif. Akif, did you understand the question?
Not sure.
Akif, we have a pipe, pipe, and water moves within that pipe. At the section 1 and 2, you see in the figure, velocity is constant, is the same. Therefore, I said this is uniform flow. Now I want to have non-uniform flow in this pipe. What does it mean? It means that velocity at section 1 should be unequal with velocity at section 2. What should I do? What can I do to have different velocities at section 1 and 2? What do you have any idea?
Maybe that our pressure increase.
By increasing pressure. Okay, that's right, for example. For example, at this point between 1 and 2, you mean here we increase pressure. Okay, yeah. By increasing pressure, definitely some characteristics will change here. Okay, Jerem, what was your opinion?
I was gonna say that if the pipe will be sloped, then it could also affect.
You mean by instead of horizontal, we will have,
or that if there could be something like sedimentation inside the pipe, it could also cause some changes by location, maybe. I'm just trying to create another idea.
No. The same sediment here will move from here. And also with a constant slope, assume this pipe. Assume this pipe with a constant slope. This is section 1, this is section 2. And velocity at section 1 will be equal to velocity at section 2 if it is steady flow. For example, in order to have non-uniform flow, you mentioned, for example, sediment, but instead of sediment, we can add some obstacle, put an obstacle here. What will be happen? You know, the velocity will change after obstacle, before obstacle. Or instead of putting an obstacle there, assume that we change the diameter. I mean, for example, the diameter comes like here, then increases like here. So velocity at here will be definitely different with the velocity of here. So you never had uniform flow in this pipe, but you can have uniform flow at this pipe or this one. Okay. The other categorization classifications for fluids are discussed in this slide. We have ideal fluid, a fluid which is incompressible and is having no viscosity, is known as an ideal fluid. Ideal fluid is only an imaginary fluid, as all the fluids which exist have some viscosity. Okay, when we say assume the fluid is ideal, it means that no viscosity, but in reality we always have viscosity. When there is no viscosity, which parameter we don't have? Mu, yeah, viscosity is mu, or mu equals to 0. When mu is equals to 0, which force can be neglected or can be deleted in our equations? Shearing stress, you remember tau, because tau equals to mu times du over dy. When mu is 0, tau would be 0, or shearing stress would be 0. Real fluid, a fluid which is possess viscosity is known as a real fluid. All the fluids in nature or in practice are real fluids. If the fluid is assumed ideal, it is not real fluid. And we divide fluids or real fluids into Newtonian fluid and non-Newtonian fluid. What is our scale to such division? Our scale is Newtonian law of viscosity. A real fluid in which the shear stress is directly proportional to the rate of shear strain or velocity is called the Newtonian fluid. Yeah. What does it mean here? The shear stress is directly proportional to the rate of shear strain. It is the formula mu times tau equals mu times du over dy. When in a fluid, shear stress tau equals to mu du over dy, or linguistically, shear stress is proportional to the rate of velocity gradient. It is called Newtonian fluid. If it is not proportional, shear stress is not proportional to the velocity gradient, it is called non-Newtonian fluids. Non-Newtonian fluid. Therefore, in non-Newtonian fluid, you cannot use viscosity law of Newton. Newton viscosity law. Okay, so the last one is ideal plastic fluid. A fluid in which shear stress is more than the yield value on shear stress shear stress is proportional to the rate of shear strain or velocity gradient is known as ideal plastic. It can be explained better here. You know, look at this diagram that summarize all fluid types. We said we have the x-axis equals to velocity gradient. This is my x-axis. And in y-axis, I have shear stress, or tau. This is tau. If tau is proportional with du over dy, it can be shown with this line, yes, which is called Newtonian fluid. If it is not proportional, it should be shown by the curve line this. It is called non-Newtonian fluid. And plastic ideal plastic, you see, for a given shear stress, this point, it is called the yield value. You have such a thing in concrete. In concrete, you know, concrete is elastic, or elasticity, strain versus stress of concrete. You have a point that's yield point. Up to that point, strain is linear, then it changes to be a curve. This is the same here. This point is called yield point. Up to shear stress, up to a given value, or for a certain value, there is no motion, or du over dy is 0. But after that yield point, again the fluid treats like Newtonian fluid. It is called ideal plastic fluid. And we also talk about ideal fluid. What is the meaning of ideal fluid? You remember? We said when we can say that mu equals to 0, it is called ideal fluid. Look, this is ideal fluid. There is change in the velocity, or we have velocity gradient, but tau equals is 0 here, yeah? Tau equals is 0 because mu is 0. And also we have ideal solid. This is when we don't have velocity gradient, it is ideal solid or a solid, which is out of the scope of our course. Okay, any questions so far? No? Now I'm going to talk about two different point of views when we use to solve problems in fluid mechanics. The one is Lagrangian approach, the second is Eulerian approach. You know, to solve any problem, we can approach to the problem in two different ways. For example, here we have such a object in front of this is assume a radar. It looks like a radar, and we have airflow around the radar, and this is flow direction shown flow direction. If we consider such a volume or control volume surrounding the radar, if we consider it, and then we say that, okay, we have flow of air from this way, which goes into our control volume. We can say this is input flow. And then we know that some flows goes out from different sides of this. It inputs from different sides of this control volume. Then it goes out from different sides of this cube. It is cube, assume, okay, from different place inputs, and we have output. Then we want to find, for example, what is the velocity or what is the force acting on it, what you should do, you should find, for example, velocity at entire control volume, one velocity, by considering the control volume as one single piece. Okay, it is called Eulerian perspective. Eulerian perspective. Just like the example that I showed you, for example, I had question in previous lectures here. Look, I showed this and I asked what is the velocity here, you know, here. I said what is the velocity here at section 1. But in fact, you see thousands or millions of water molecules are available at section 1, yes? Each molecule can has different velocity. But I said at section 1. And entire section was considered as a unit, as a single object. This is Eulerian perspective. What is the Lagrangian perspective? In Lagrangian perspective, I think another, which one? Yeah. In Lagrangian perspective, as you see here, we deal with any single water molecule one by one, point by point. For example, I can say that, for example, velocity is of this point, or I can calculate velocity of this point or velocity of this point, and also I monitor motion of fluid by time. I say that this fluid at this point of the control volume has the velocity of x. Here velocity is y, here is velocity of is z, blah, 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 blah. So you see that I monitors entire molecules within the control volume. So this is called Lagrangian fluid. I'll give you more sensible example, a more sensible example. And assume that you are watching a football match, okay? You are watching a football match. Actually, you only watch a TV, okay? This is your TV, okay? And 24 players, each of them are located at different part of the field, stadium, okay? But you only look at your TV, which shows just one perspective of one camera, yeah? And you, in that TV, maybe one player comes with ball, then it moves, okay? If the cameraman does not change the view of camera to monitor the ball, you cannot see what will be happen after 2-3 seconds. Player moves out of the camera. When the camera is constant, you just see a TV frame. It is called Eulerian. When camera moves to trace the ball, to see really where is the ball, it is Lagrangian. Okay, which one, now the question in your mind, which one is more convenient? Which one is more convenient? Eulerian or Lagrangian? When the cameraman fixed the camera at one angle and moves to home, it could be more convenient. Therefore, Eulerian is convenient. But in Lagrangian, the cameraman should follow the ball every second. Therefore, Eulerian perspective is more comfortable than, or more convenient than Lagrangian perspective. And I have a question here. For example, in this pipeline, if I ask you what is the velocity of this pipeline, can you answer it? My question, what is the velocity of water moving in this pipeline? Can you answer it? Maybe you cannot. Why? Because there are several different sections, several places. Look, here we have diameter of this value. The diameter here is less than the upper one. Here we have a bend. Therefore, velocity varies from here to here. And if it is closed, the velocity is zero actually. Here the velocity could be zero if it is closed. But water can move downward, yes? Therefore, to be able to answer to this question, you need to ask me where. Professor, where do you mean? Velocity where? And in that case, I have to show you a section. Okay, I can say here, I mean here, or here, or at here. Okay, in that case, you can answer. Okay, to answer what is the velocity here, now you need a control volume. Control volume. Let's show it by green. You can say that, okay, I consider this bend as a control volume. As a control volume. I know that some water goes within from here, some water goes out from here. Then by using physical equations, physics, by using some equations that I will teach you in the future, you can find velocity within the bend. I hope with this example you got the message or got the concept of the control volume. Okay, I'm going to give you about 45 minutes break, okay? Because I have a meeting just now, started the meeting. After 45 hours, I will come back to continue today's lecture. 45 minutes. We will meet each other at 2:45. Okay? Have a good day. Bye for now.